Prop 34 says, in parallelogrammic areas, the opposite sides and angles are equal to one another, and the diameter bisects the areas. Yeah, it's kind of a tough word for me to say. Parallelogrammic. It doesn't come up very much, and somewhat annoyingly, parallelogram is not even defined by Euclid. It's just sort of assumed that you understand what's meant, which I think it's very strange that it's not defined. I don't know why, because some other things that I think are even clearer, clearer definitions or need less defining, he defines them. Parallelograms, he doesn't define them, so assume that parallelogram or parallelogrammic areas means some area that is bounded by parallel lines. So in particular, we'll assume that we've got this sort of figure where AB is parallel to CD, AC is parallel to BD. And what do we want to prove? Well, we just want to prove that the opposite sides are equal. So this is kind of like, in comparison to the last proposition, we assumed at the outset that like A, B, and C, D are both equal and parallel. Here we're not saying that. We're not assuming that they're equal at all. We're just saying assume that AB is parallel to CD, AC is parallel to BD. Then what we have to prove, on the one hand, opposite sides are equal, so we need to prove AB equals CD and AC equals BD. We also need to prove that opposite angles are equal. So just kind of shorthanded, angle A is equal to angle D, angle B is equal to angle C. So that's everything that we need to prove here. Oh, right. That's not everything that we need to prove here. The maybe more interesting, what I think is at least the more interesting claim, is that the diameter bisects the areas, which on the surface, at least when I first look at that, I go, oh my gosh, how are we going to prove that? But it's pretty intuitive. When we get there, it's nice and straightforward. It's pretty quick and intuitive. Okay, let's do it. So first things first, really similar to what we did last time. I guess I already added in BC. Yeah, I set up these diagrams before I start, and I apparently just mindlessly added in BC. That's actually not part of the original figure. That's part of our construction for proving this. Sorry, that does make things a little bit more confusing. But let me at least write out what we're given. So we'll assume that, and I should be sort of precise here. This is not stated. Euclid doesn't state that ABCD is a quadrilateral. Let me see what he says, because I believe he actually calls it a parallelogram in here. So, right, so let me just read kind of like the first few lines of the setup. He says, let ACDB be a parallelogrammic area and BC its diameter. Okay, so I guess it kind of is already in there. BC is in there. But more. He says, I say that the opposite sides and angles of the parallelogram ACDB. So he even calls this a parallelogram. Because we haven't really defined parallelogram, I feel like I would prefer to say ABCD, and I guess he's going counterclockwise with his lettering. I'm going to go clockwise. ABCD is a quadrilateral, such that or with, so such that, I'll say such that AB is parallel to CD and AC is parallel to BD, and I'll say with BC its diameter. Okay, that makes me feel a little bit better about already having that line in there. It really doesn't change anything. It's just like the perfectionist side of me coming out. Yeah, so there we go. Yes. Okie dokie. So that's the setup. ABCD is a quadrilateral with AB, opposite sides are parallel. BC is its diameter. Okay, how do we prove this? Well, since AB is parallel to CD, what can we say? We know something about the angles. And I guess I could say more, since AB is parallel to CD with BC crossing it. But I think it's kind of implied. We get that angle ABC is equal to angle BCD. So ABC, this angle right here, is equal to BCD, that one right there. And where does that come from? That comes from Prop 29. Since we're given that the opposite sides are parallel. All right. And again, since kind of reorienting, since AC is parallel to BD, we also can say something about some other angles. We can say that angle ACB equals angle CBD. And again, that comes from Prop 29. So ACB equals CBD. Yeah, that looks about right. Okay, and both of those just come from Prop 29. Okay, so, well, why is that helpful for us? Let's look at what we have. We have that ABC, this angle right here, is equal to this angle right here. We have that ACB, this angle right here, equals this angle right here. And then they have this side in common. So we're looking at an angle, side, angle situation. And we have a proposition for that. Which one was it? I believe, let's see, it's proposition 26, not even that long ago. Let's see. So I guess I should just sort of restate it, since ABC equals angle BCD, angle ACB equals angle CBD, and the obvious one, BC equals itself. And let's see here, because the way that I think about this and the way that we kind of think about it now today is that because we have this, we have angle, side, angle, and we know that those are, that's a congruence. There's a congruence between the triangles, but technically the proposition doesn't say that. Like, for us to get that congruence of angle, side, angle, we're actually kind of putting together a couple of propositions. So it's Prop 26 in conjunction with Prop 4. Those ones together tell you that the triangles are congruent, because Prop 4 is the only one where he actually says the triangles are congruent. So the conclusion, though, of Prop 26 is that because we have this angle, side, angle situation, the two triangles will also have the remaining sides equal to the remaining sides, and the remaining angle equal to the remaining angle. So since this is the case, I'll say we have, and what does he say? Right. AB equals CD. AC equals BD. And this does end up being kind of a key piece here. We know that angle BAC equals angle CDB. So BAC equals CDB. So that gives us quite a lot of what we needed, because this is saying that, okay, yep, opposite sides are equal, and at least angle A is equal to angle D. That's kind of really all that we need, because I would say, like, if I was writing this proof myself from here, because we have these triangles equal to each other, this is Prop 26, because we basically have angle, side, angle, maybe we can just invoke Prop 4 to say, yeah, okay, these triangles are equal, so that literally gives us everything else that we need. But how does Euclid state it? So he says, and again, since angle ABC equals angle BCD, and angle CBD equals angle ACB. So just again, really quickly to see what we just said, ABC, so this angle is equal to BCD, And then CBD, this angle right here, is equal to ACB. By common notion 2, equals added to equals are equals. It follows that, let's see, maybe I should just be sort of explicit, angle ABC, so ABC plus angle CBD equals angle BCD plus angle ACB. That is angle ABD equals, so ABD equals ACD, I guess. All right, because this left-hand side ABC plus CBD is ABD, and same thing with the right-hand side. So there, now we've proven all of the opposite sides are equal, opposite angles are equal. Looks like the video is like kind of lagging behind what I'm saying, in case it looks a little bit funky, right? So we've proven everything, opposite sides and angles are equal. We just have to show that the diameter bisects the diameter. And how do we do that? Well, let's see, I'll follow along with what he says rather than doing my own thing. Since AB equals CD, BC equals BC, and angle ABC equals angle BCD. We have the whole conclusion of prop 4, but the main one that we need right here is that the triangles are congruent. Triangle ABC is congruent to triangle BCD. Let's see, I better make sure ABC is equal to BCD. Yeah. Yeah, they're congruent, that is, which is by prop 4. And well, what does that mean? ABC plus BCD, those two triangles together make the full quadrilateral ABCD. So BC bisects the area of ABCD. And that's what we needed to prove. QED, therefore, etc.